Okay, we are in the midst of chapter 24, oxidations, and we're about to dive off into the land of tearing things asunder. Now you may have noticed that I'm trying to make these mini lectures even more mini, so that's why there's so darn many of the mini lectures. So let's get going. Oxidative cleavage can be done by a whole big variety of oxidants. So I've got to tell you, it does seem a little confusing. I'm going to try and make it as sensible as possible. The big overview is really presented on this slide. Now we've already seen permanganate. We know it's a great oxidant. We know that permanganate, that manganese atom right there, is in a very high oxidation state of +7. We know that there's a lot of oxygens on there, so it's just screaming, oxidize me. We know that the pi electrons are electron rich. Hey, this all says oxidation. What you need to pay attention though here is that we're under kind of mild-ish conditions. It's cold, and as a result what we end up with is the syn diol, which we've already seen. Now if we tweak it up just a hair, and instead of using cold permanganate, we heat it up, then look out. Now all of a sudden, boom, we tear open our alkene and we get oxidative cleavage. What you can see here is that I'm basically getting a ketone right here, and at the other side I'm making a carboxylic acid, and we will soon see why we get the two different functional groups on the two different carbons of the alkene. So permanganate and heat, oxidative cleavage. Osmium tetroxide. Wait. I thought osmium tetroxide gave us a syn diol. Well, it does, but in a subsequent step, if you add sodium periodate, this set of reagents too will lead to oxidative cleavage. And what we want to point out right here is, whereas hot permanganate gives you the carboxylic acid, this osmium tetroxide sodium periodate combination gives you the aldehyde. Finally, well, and I should point out that we aren't pulling any fast ones on you. The osmium tetroxide does give you the syn diol. It's just that the sodium periodate then reacts with the diol to do the cleavage reaction. Alright, finally, one more set of reagents for cleavage, and that's ozone. And what we want to point out here is that ozone gives you the flexibility of going to either the carboxylic acid or the aldehyde, depending upon what workup you use. So that's the whole big picture of oxidative cleavage. Now, this will be the last mini lecture, but let's look at the other two in some detail. Actually, all three of them do have some common features. All of them have addition of an oxidant to the alkene. Well, now, that's kind of a lie. It's the periodate, like I said, adds to the diol. But basically, it's that cycloaddition of the oxidant to the alkene that we saw in the previous mini lectures. Okay, then what? Well, then, once you've got that oxidant added to the alkene, so here we had this alkene, and I added some oxidant, well, you get this weird looking intermediate, 5-membered ring. Now, what happens to that intermediate is it falls apart, and it falls apart in what's called a cycloelimination. Now, pay really close attention to these arrows. That red arrow right there is telling you I am making a carbon-oxygen double bond there. And if I slap up that bold set of sigma electrons, then something's got to give, and that's where the ZO bond breaks. Okay, so we've got all three of these electron movement arrows happening at once. The blue arrow is showing you that yes, I'm making a CO double bond on that carbon-oxygen bond there. And the bottom line is that bold sigma bond is being broken. So this is what you get. Cleavage, just like we said, boom, that is torn apart and you get the two carbonyls. So the alkene is broken in two. What we have to deal with are two issues. The first one is how many products are formed, and the second one is what kind of product is formed. What stays common is that you get a carbonyl. Absolutely, positively, you're always going to get a carbonyl. But do I get an aldehyde or do I get a carboxylic acid? All right, now how many products are formed is addressed by looking at the nature of the alkene. If the alkene is just part of an acyclic molecule, well, when you cleave that in half, well, I mean when you cleave the double bond, you just basically get two pieces. And you put your oxygens there. There they are. Piece 1, piece 2. But what if your alkene is part of a ring? Well then, when I cleave it, I get this, put my oxygens in there, and what you can see, well, this whole thing is all tied together. So if it's an acyclic alkene, I get two pieces. But if it's a cyclic alkene where the double bond is part of a ring, you get one piece, one product. Okay, so that's a kind of a handy thing to keep in mind when you're thinking about ozonolysis and these oxidative cleavages. All right, well now what about what kind of product? Well, that depends entirely upon the presence of that bond, a vulnerable carbon-hydrogen bond. This right there is what is susceptible to further oxidation. So if you have an alkene that has a hydrogen on it, that's where you're going to have to worry about further oxidation. If you have an alkene that only has carbons on it, that's going to give you a ketone, always going to give you a ketone, nothing else can happen. So let's look at some examples. Potassium permanganate and heat. The whole point of potassium permanganate and heat and why we get carboxylic acid is because once it oxidizes up to the aldehyde, there's no stopping it. So it goes all the way to the carboxylic acid under these conditions. Here's a nice example. We've got a steroid framework here. We have our pi electrons, electron rich. We have our very strong oxidant that's looking for something to oxidize. Hence, we look at the alkene. But what we really want to pay attention to here is the fact that it's hot. So we cleave our double bond. We put an oxygen here. And since this guy over here is a ketone, is to a pair of carbons, we end up with a ketone. But how about the bottom part of the alkene? There's that vulnerable vinyl hydrogen, so it gets oxidized all the way up to the carboxylic acid. All right, that's example number 1. Example number 2. What happens when we do oxidative cleavage on an alkyne? Well, my cute little demo of pulling the alkyne apart and putting oxygens on there actually is pretty wacky, but it's still kind of helpful, if that makes sense. So looking at an alkyne, let's make it a really big alkyne. Here's my alkyne, R and R prime. So I just erase the middle out of it, and then I put my oxygens on. Well, that looks pretty ridiculous. Who's ever heard of such a thing? Well, it's kind of like this, right? But 3 carbon-oxygen bonds would be the same thing as carboxylic acid. So when I do look at cleavage of a triple bond, I am looking at, boom, no matter what the reagents are, I'm going to get 2 carboxylic acids. Now, that was an alkyne that was not part of a ring, so of course I'm going to end up with 2 pieces, one on the left, one on the right, and I really meant to say one on the right, one on the left, whatever. But turns out Frida Chemist only found this one. Where did the other product go? Well, sometimes we don't really care about these little pieces, and as you can see, that is ethanoic acid, aka acetic acid, aka something that is very soluble in water, and that would probably just get removed and washed away in your aqueous workup. Okay, so that was permanganate. What about periodate? Well, we said periodate is the one that gives us the aldehyde, and here's an example. Exactly right. First step makes the syn diol. Second step, we add sodium periodate and it cleaves my double bond into 2 pieces. Because this is all part of a ring, there's not 2 pieces, they're all tied together. So I end up with 1 molecule but 2 carbonyls. And then finally, this last step is just the workup that gets rid of the oxidant. How does this work? Well, as I said, the osmium tetroxide makes the diol. The diol reacts with the sodium periodate, and that gives you this funky looking iodo thingy-do. Yeah, that's the official scientific language, trust me. And that iodo thingy-do can then do the old cycloreversion thing, right? Boom. I can't barely fit this in here. Zoop, up to there, and then down to there, and that's what takes you to your 2 carbonyls. All right, that's it for this mini lecture. We're just going to wrap it up with some examples. We'll get to ozone in the last mini lecture. Fill in the missing information. All right, nucleophile. Oops, it's not what I wanted to do. Nucleophile. What do I need to add? Looks like I'm adding the elements of H and O and H. In other words, water. But water is not a strong enough acid to react with an alkene, so I must have a catalytic amount, maybe H2SO4. And that will give me electrophilic addition of water across the double bond. I could also do this with oxymercuration. You might want to ask yourself, why does the OH end up on that carbon and not here? Question number 2. Fill in the missing information. What do I get when I add osmium tetroxide in the presence of hydrogen peroxide with T-butanol as a co-solvent? No periodate added. Yep. I'm just going to get a Halloween colored syn diol. Looks good. And of course you can approach from the top side or the bottom side, so I get a racemic mixture here. What happens if I go ahead and then add sodium periodate to that syn diol? Then we will end up with oxidative cleavage, but it's milder than permanganate. So let's just emphasize 1, 2, 3 carbons here. There's my cleavage. So 1, 2, 3. There's my other carbonyl. and it too will be an aldehyde. So I end up with a dialdehyde, only one product, because the alkene was part of the ring. All right, fill in the missing information. What does it look like is happening? Clearly I am going from H, H to, lots of H's, a reduction. So that tells you right away I'm going to add H2. H2 by itself will not do diddly squat. I need to have a transition metal catalyst, so hydrogen and palladium would work wonders. Ah, now what? I have this funky looking aromatic alkane dilly. How do I get a bromine there? Ugh. I have two hydrogens here. That's neither an electrophile nor a nucleophile. How am I going to replace one of these hydrogens with a halide? Think radical. Okay, this is exactly where radical chemistry comes in. And basically, this is similar to, basically the same thing as an allylic halogenation. This is not allylic, but it's benzylic, so I know I need to add NBS and light or heat, and I will get a great yield of my allylic/benzylic halogenated alkane. All right, how about this guy? Oh, this is better yet. If I go from this alkene to this alkane to this alkyl halide, how do I go from this alkyl halide? Oh shoot, that's kind of stupid, because that's what I started with. But let's pretend like I didn't start with it. How would I go from the halide to the alkene? How about a strong base and heat to get the elimination reaction? And then finally, how do I go from the alkene to my, this is not a syndiol. Osmium tetroxide will not work. Permanganate will not work. You know? Make the epoxide, open it up, anti-addition across the epoxide. Good little review for you. That's it for this mini lecture. We will look at ozone to wrap things up in the next mini lecture.